Hello, everyone. So last time we were still doing number theory, and we looked at congruences and how to solve congruences. So last time we solved congruences. So a particular form of congruence that we looked at last time, and we provided an algorithm to solve it, was a linear congruence of the form, let's say AX is congruent B mod M. And we also looked at system of congruences, which we called it, Chinese remainder theorem. So Chinese remainder theorem looked at a system of congruences. Let's say if you want to solve 3 congruences at the same time, how can you solve it? So we provided an algorithm also how to find the value of X that satisfies, let's say, 3 given congruences or 5 given or n given congruences at the same time. Now, this time we want to look at, so the next topic, Fermat's little theorem, 4.4.5, Fermat's little theorem. So Fermat, was a French mathematician who lived in 17th century. And there are 2 famous theorems called Fermat's theorems. So one is called Fermat's little theorem, which is easy to prove. We'll prove it today. We'll state and prove today. And another Fermat theorem, maybe you have heard about it, is called Fermat's last theorem. So Fermat's last theorem was one of the most complicated unsolved mathematical problems, but not just in number theory, in whole mathematics. And mathematicians, spend so many times, great mathematicians spend so many times to solve Fermat's last theorem, but they were unable to do so until just a few years ago, around maybe, I think less than 30 years ago. So they thought about it for centuries, and just less than 30 years ago, it was proved, Fermat's last theorem. So Fermat's last theorem is a very complicated problem. It was open and unsolved for centuries and solved just around 30 years ago. But Fermat's little theorem, it is very important, but a simple fact and easy to prove, and we'll provide a proof for it today. So before that, we have to look at polynomials. I think you are familiar with the concept of polynomials. So recall a polynomial let's say is a function of the form, let's say p of x equals an x to power n plus an minus 1 x to power n minus 1 plus a1 x plus a0, where an is not equal to 0, and a0 to an are real numbers. And n is a non-negative integer called degree of p of x. So n is equal to degree of p of x. So this is the definition of polynomial. But right now in number theory, we look at polynomials with coefficients, with integer coefficients, and in particular with coefficients chosen from the set Zm or Zp, mostly Zp, where p is a prime number. So let me explain about this. So in number theory, polynomials with coefficients chosen from the set Zp equals 0, 1, 2 to p minus 1. Polynomials with coefficient chosen from this set are considered so p of x equals an x to power n plus all the way to a1 x plus a0, and an to a0, they're all in Zp, this set. So p here is a prime number with p a prime number. And so still the leading coefficient an has to be not equal to 0 in Zp. So when can we say that two numbers in Zp are equal? So you can probably guess what this means, that two numbers are equal in Zp. So note a equals b in Zp if a is congruent b mod p, i.e. if p divides a minus b. So Zp is has an important role in number theory, where p is a prime number. So we have many Zp's because we have many prime numbers. But for each prime number, if we consider the set 0, 1 all the way to p minus 1, this is a set with p elements. So this is called Zp. Now, two numbers are equal in Zp if those two numbers are congruent mod p. So for example, 5 is equal to 2 in Z3 because 5 is congruent to mod 3, right? Because 3 divides 5 minus 2. Therefore, 5 and 2 are equal in Zp or in Z3 in this case. Okay, so let's look at an example. So an example of a polynomial in, let's say, Z5. So give me an example of a polynomial in Z5. So still polynomial is it has the same definition as before. So the only difference is that in high school and in pre-calculus, when you talked about polynomials, the coefficients were chosen from set of real numbers. This time the coefficients are integers, and not only integers, but also in Zp for some fixed prime number p. And what is Zp? Zp is a set with p elements consisting of 0, 1 all the way to p minus 1. So Z5 means a set with 5 elements consisting of 0, 1, 2, 3, and 4, right? And now I want to consider a polynomial, let's say P of X, whose coefficients are chosen from Z5. So coefficient from Z5 means either 0 or 1 or 2 or 3 or 4. But please remember that the first coefficient is not allowed to be 0, the leading coefficient, right? See, even in high school definition of polynomial, the leading coefficient, an, is called leading coefficient and is not allowed to be 0. Still, the leading coefficient is not allowed to be 0. So I can say, for example, let's say x to power 4, for example, plus 2x cubed plus 3x squared plus 4. So this is a polynomial of degree 4. Or I can do another example. Let's say P of X equals 2x to power 6 plus x squared plus 3x plus 1. So this is a polynomial of degree 6 and degree 6. Okay, so these are examples of polynomials in Z5. Okay, now what is the meaning of a root of a polynomial? So root of a polynomial, again, is another concept that we have seen in high school and in pre-calculus. Root of a polynomial means, let's say a number a such that a root of a polynomial, let's say P of X, a number a such that P of A equals 0, right? That's the meaning of root of a polynomial or 0 of a polynomial. A number that when you replace X with that value, you get 0, right? For example, X equals 2 is a root of P of X equals X squared minus 4, right? Because when you replace X with 2 in P of X equals X squared minus 4, you get 0. Now, what's the meaning of root of a polynomial P of X in ZP? So this is the meaning of root of a polynomial in the high school context and pre-calculus context. But what about the meaning of root of a polynomial in ZP? So I think you can guess now. So root of a polynomial in ZP again, root of a polynomial, let's call it again P of X. Again, it's a number a in ZP this time. So see the only difference. Okay. Let's compare it with the previous case. When we talked about just a polynomial in a high school context compared to a polynomial in ZP. Polynomial in ZP has the same definition as the standard polynomial. The only difference was the fact that we required the coefficients to be chosen from ZP. And what was ZP again? The set consisting of 0, 1, all the way to P minus 1. Now this time, root of a polynomial means any number a, any real number a that P of A equals 0. But root of a polynomial P of X in ZP, so now you can probably guess that means a number a, but this time a has to be chosen from ZP, because when we say a polynomial in ZP, our universe is just ZP. We are not allowed to choose any number outside ZP. Normally in high school, when you say polynomial, your universe is real numbers. You can choose any real number as coefficients or as the inputs of X. But when we say polynomial ZP means we have changed our universe. Our universe is now only the set consisting of 0, 1 to p minus 1. So for the coefficients and for the values of x, we are not allowed to choose any real number anymore. We have to choose a number from this set ZP. ZP is now our new universe. So a number, so root of a polynomial P of x in ZP means a number A, this time is ZP, such that P of A equals 0 in ZP. So equality to 0, now, as I said, my universe is now ZP. So equality to 0 is now in ZP. What is the meaning of equality 0 in ZP? I just told you a few minutes ago that equality of two numbers in ZP has the meaning that those two numbers are congruent mod P, meaning that P has to divide the difference between those two numbers. Okay, so root of a polynomial is a number A such that in ZP such that P of A equals 0 in ZP. And what's the meaning of P of A equals 0 in ZP, i.e. P of A is congruent 0 mod P. That's another way to say P of A equals 0. And another way to say this is P divides the difference between P of A and 0, which means P divides P of A minus 0, which means P divides P of A. So let's look at an example. Let's say P of x equals x squared plus 5x plus x in, let's say, Z7x, or in Z7 as a polynomial in Z7. So P of, let's look at, for example, P of 1. So question, let me ask you a question. So let's this, is x equals 1 a root of P of x? So normally in high school, if you're, so if x squared plus 5x squared, let's say, for example, x cubed plus 5x squared plus x. If in high school, let's say your teacher gave you this polynomial, P of x equals x cubed plus 5x squared plus x, and they asked, for example, is x equal 1 a root of P of x? Well, to answer this question, you have to replace x with 1. If I replace x with 1, I get 1 cubed plus 5 times 1 squared plus 1. And that's 1 plus 5 plus 1, which is 7. And then 7, P of 1 is 7. And then you say, okay, therefore 1 is not a root because P of 1 is 7. It's not 0. In order to have a root, P of that number must be 0, right? But P of 1 is 7, it's not 0. And, and then you would say that, therefore 1 is not a root. That's what you would say in high school. But right now I am looking at P of x as a polynomial in Z7. So my universe is now Z7. Everything is mod 7. So P of 1, if I want to know 1 is a root of P of x as a polynomial in Z7 or no, I have to look at P of 1 again. How much is P of 1? So P of 1 is, as we said, 1 cubed plus 5 times 1 squared plus 1, which is 7. And 7 is equal to 0 in Z7. Seven is not 0 as two integers or two real numbers, but in Z7, 7 and 0 are equal. Why? Because again, what is the meaning of equality of two numbers in ZP? two numbers are called equal in ZP if they are congruent mod P. So are 7 and 0 congruent mod 7? Does 7 divide 7 minus 0? Yes, 7 divides 7 minus 0 because 7 divides 7, right? So this is equal to 0 in Z7 since 7 congruent 0 mod 7 because 7 divides 7 minus 0. And therefore that means x equals 1 is a root of P of x. As a polynomial in Z7. Okay. So now one question that we could ask here is that given a polynomial of degree, let's say n, how many roots can we have for P of x? So a polynomial of degree n in ZP can have how many roots? So question. Let me say number of roots of a polynomial So a polynomial P of x of degree n has, so this is basically a theorem, so we call it theorem, has at most n real roots. So proof of this is in pre-calculus course. So when you look at polynomial in the standard concept, as a standard concept of polynomial, a polynomial of degree n has at most n real roots. So a polynomial of degree 2, for example, a quadratic function, has at most 2 real roots. Or a polynomial of degree 3 has at most 3 real roots, and so on. So this is a fact that you learn. It's a implication of division algorithm for polynomials. Division algorithm for polynomials. You can use it to prove this theorem. I normally prove this in my Math 100 class, pre-calculus course. But what happens if you look at the polynomial as a polynomial in ZP? So can we still say that this theorem is still valid? So another theorem. This theorem is called Lagrange theorem. A polynomial P of x as a polynomial in ZP with degree n has at most n roots in ZP. Well, that's amazing. This theorem, which is called Lagrange theorem, Lagrange was a famous mathematician, and there are different results after his name in different fields of mathematics. So for example, Lagrange multiplier method, I think you have seen this in your calculus course. But I mean, different results are after, as I said, Lagrange in mathematics. In number theory, Lagrange theorem is this theorem, which says a polynomial of degree n in ZP has at most n roots. So still the same theorem that we said, that you learned in pre-calculus, when you look at the polynomial as a polynomial ZP, still the same theorem, still the same result is valid. But this time, of course, the roots are the numbers. When you look at the polynomial as a polynomial ZP, the roots must also be in ZP. And how many of them can we have? At most n of them, if the polynomial is of degree n. So let's look at an example of this. Such a simple example, let f of x equals, let's say, x squared plus 1. Let's say p of x equals x squared plus 1 as a polynomial in Z5. How many roots does p of x have? So Z5, we know that. What is the meaning of Z5? Z5 is a set. Yeah. P of x equals this. How many roots does P of x have? Z5 means the set consisting of 0, 1, 2, 3, and 4. Now, Lagrange theorem says that a polynomial of degree n in Zp, if p is prime, well, here 5 is prime, a polynomial of degree n has at most n roots. What is the degree of p of x? Degree of p of x here is 2. So p of x can have at most 2 roots. So there are 5 potential candidates for roots, which are 0, 1, 2, 3, and 4. But according to Lagrange theorem, at most 2 of them, at most 2 of these out of these 5 numbers can be a root for p of x. So let's verify this. So if x is equal to 0, p of 0 is equal to 1, and is 1 equal to 0 in Z5? Equality in Z5 means congruence. Is 1 congruent 0 mod 5? Does 5 divide 1 minus 0? No, 5 does not divide 1 minus 0. So these two are not equal, therefore 0 is not a root. Now let's check the next number. If x equals 1, p of 1 is equal to what is that? 1 squared plus 1 is 2. 2 also not equal to 0 in Z5 because 2 is not congruent 0 mod 5. If x equals 2, p of 2 is 4 plus 1, which is 5. Is 5 equals 0 mod 5 in Z5? In other words, is 5 congruent 0 mod 5? Yes, 5 is congruent 0 mod 5. So that means x equals 2 is a root. Now let's check the next number. P of 3 is 9 plus 1. 9 plus 1 is 10. Is 10 equals 0 in Z5? Yes, 10 equals 0 in Z5 because 10 is congruent 0 mod 5. And finally, if x equals 4, P of 4 is 16 plus 1, 17, which is not equal to 0 in Z5. So how many roots do we have? So there are 2 roots for p of x equals x squared plus 1 as a polynomial in Z5. Namely, what are those 2 roots? Namely, x equals 2 and x equals 3. As predicted by Lagrange theorem above, a polynomial of degree 2 has at most 2 roots. Seems that my screen was freezed. So there are 2 roots for p of x equals this as a polynomial Z5, namely x equals 2 and x equals 3. And as predicted by Lagrange theorem, a polynomial of degree 2 has at most 2 roots. Here, this was the polynomial of degree 2. This is the degree of this polynomial is 2, and it must have at most 2 roots. And it had 2 roots. Which 2 roots? 2 and 3, because p of 2 and p of 3 were 0 in Z5. Okay, so there are some interesting applications of this Lagrange theorem and polynomials in ZP. So let me state one of the book exercises. So question 17. Of this section, 4.4. Show that if P is prime, the only solutions of, then the only solutions of x squared congruent 1 mod P are integers such that x congruent 1 mod P or x congruent minus 1 mod P. Okay, we can solve this question with at least 2 different methods. So let me explain about this. So solution 1, because your book does not mention about this Lagrange theorem. So that's why we can solve this question without using Lagrange theorem as well. So my first solution is that, so what do we want to solve? We want to solve x squared congruent 1 mod P. So x squared congruent 1 mod P is same as saying that P divides the difference between x squared and 1, which means P divides x squared minus 1. And this is same as saying that P divides x minus 1 times x plus 1. And we know from, I think, 2 lectures before that if P divides AB, then P divides A or P divides B. Right? If P is prime and divides AB, this is a very important fact. We stated this 2 lectures ago, but we also used it last lecture as well. That if P divides AB, then P divides A or P divides B. So here I can say that P divides x minus 1 or P divides x plus 1. And this is same as saying that x is congruent 1 mod p or x is congruent -1 mod p. P divides x minus 1 or p divides x plus 1. This is p divides ab. This is like your a, this is like your b. And p divides ab means p divides a or p divides b. And now p divides x minus 1 is same as saying that x is congruent 1 mod p. And p divides x plus 1 is same as saying that x is congruent -1 mod p, because the meaning of, again, x congruent 1 mod p is what? Is that p divides the difference between x and 1, means p divides x minus 1. And similarly, this is same as saying that p divides x minus -1, which is same as saying that p divides x plus 1. Well, that's it. So we showed that the only solution, so that's the only solution or solutions for x squared congruent 1 mod p are integers x such that x congruent 1 mod p or x congruent -1 mod p. Now, solution 2, I want to use polynomial. Solution 2, I think it's nicer and more beautiful. So solution 2, x squared, we want to solve x squared congruent 1 mod p. So this is same as saying that x squared -1 congruent 0 mod p. Now I want to look at this as a polynomial. So this is same as saying that p of x equals, I want to define x squared -1, my polynomial as p of x. And this is same as saying that this polynomial equals 0 in ZP. X squared -1 congruent 0 mod p is same as saying that x squared -1 equals 0 in ZP, because again, I repeated many times today that the equality of two numbers in ZP means that those two numbers are congruent mod p. Now, I want to find the roots, so we want to find the roots of p of x equals x squared -1 in ZP. So x equals 1 is one root, a root of p of x, because p of 1 is equal to 1 squared -1 equals 0. X equals -1 is also a root, because p of -1 equals -1 squared -1, that's also equals 0. They are equal to 0, so they're also equal to 0 in ZP. So that means these are two roots Well, you may tell me that -1 is not one of the numbers in ZP, because ZP was started from 0, 1 all the way to p -1. But yes, -1 is not in that list. But I can find the equivalent number to -1 in ZP by just adding p to my number. So I can also say, because everything is ZP in ZP, so everything is mod p, right? So -1 is same as p -1. When you talk about congruence mod p or equality in ZP, means every calculation is done mod p. Therefore, when you talk about -1, that's same as talking about p -1. Because if you add p to a number, it's like adding 0, right? P is 0 mod p, right? So when you add p to a number, it's like adding 0 to a number, which I am, of course, allowed to do that. So when I say x equals -1, I can also replace it with p -1. So P of, you could also write -1 here, it doesn't matter, you could say P of P minus 1 equals P minus 1 squared minus 1, and that's -1 squared minus 1, which is also 0. So like I said, P is 0 in ZP. So P minus 1 is same as -1. So we have 2 roots in ZP. But how many roots can we have in total? What was P of X? P of X is x squared minus 1, is a polynomial of degree 2. A polynomial of degree 2 can have at most 2 roots. And I already found 2 roots. So that means these are all the roots that I possibly can have them. There can be no other roots because the polynomial has at most 2 roots, and I already found 2 roots. So that means these are all the roots. There cannot be any other roots. So since P of X equals x squared minus 1 is a polynomial of degree 2, it can have at most 2 roots in ZP. This is Lagrange theorem. So that means x equals 1 and x equals -1 are the only roots in ZP. Which is same as what the question was asking. The question was saying that, show that the only solutions are numbers x such that x is congruent 1 mod p or x is congruent -1 mod p. But x congruent 1 mod p means what? It means x equals 1 in ZP. And the other one is x equals -1 in ZP. So -1, of course, as I said, is same as p minus 1. Are the only roots in ZP. Right, so, and that's exactly what the question was asking us to show, that x equals 1 in ZP and x equals -1 in ZP are the only solutions in ZP. Okay. Now let's look at Fermat's theorem. Fermat's little theorem. So let A be any integer such that P does not divide A, then A to power P minus 1 is congruent 1 mod P. Okay. And furthermore, A to power P minus 1 is congruent A mod P for every integer A. So before giving examples and also proving this, let me state this theorem as equality in ZP. So another version, if A is not equal to 0 in ZP, right? So when you say P does not divide A, that means in ZP, A is not equal to 0. Because remember, A equals 0 in ZP means what? Means P divides the difference between A and 0, which means P divides A. So if P does not divide A, means A is not equal to 0. So if A is not equal to 0, then A to power P minus 1 equals 1, again in ZP. See, this is, I think, nicer, right? If a number is not 0, so when I change my universe to ZP, which means the set consisting 0, 1 to P minus 1, then any number to power P minus 1 is 1, is equal to 1. Well, of course, 0 cannot be 0 to power P minus 1 remains 0. So I have to exclude 0. But other than 0, any number to power P minus 1 is equal to 1 when my universe is ZP. So it's very interesting, right? Because when my universe is the set of, for example, integers, so any number to power P minus 1 equals, so only 1 and minus 1 to power P minus 1 will be equal to 1. Assuming that, P is not 2. But other numbers to power P minus 1 are not 1, right? So for example, let's say if P is 5 and A is 4, 4 to power 4 is not 1, of course. Or 3 to power 4 is not 1. But when I change my universe to ZP, when all my calculations are mod P. So what's the meaning of changing universe to ZP? Means if all my calculations are done mod P, then any number to power P minus 1 equals 1, of course, except 0. So in other words, if we set P of x equals x to power P minus 1 minus 1, then what are the roots of this polynomial as a polynomial in ZP? Then, so let me say, if we set this as a polynomial in ZP, then the roots of this polynomial are 1, 2, 3 to P minus 1. So this is another, I said in other words, but you could also say another version if you want. Another version. So this is very interesting. Look at this polynomial, x to power P minus 1 minus 1. It's a polynomial of degree P minus 1. Lagrange theorem says that this polynomial can have at most P minus 1 roots in ZP. And Fermat's theorem says it actually has P minus 1 roots. Which P minus 1 roots? Every number except 0. Because Fermat's theorem says that for every number except 0, A, if A is any number except 0, then A to power P minus 1 equals 1. But what is the meaning of A to power P minus 1 equals 1? It means A to power P minus 1 equals 0. Which means P of A equals 0. Look at here, I define my P of x to be x to power P minus 1, right? So what is P of A? P of A will be A to power P minus 1, which is P of A is A to power P minus 1, which is 0 according to this equality. a to the power p minus 1 equals 0 according to this equality, which means p of a equals 0 for every number a except 0, which means every number a except 0 is a root for this polynomial. Therefore, the roots of this polynomial are 1, 2, 3, all the way to p minus 1. So this is a fact, so which is consistent with Lagrange theorem. Lagrange theorem said that a polynomial of degree p minus 1 can have at most p minus 1 roots. And this theorem guarantees that for this polynomial, we actually have p minus 1 roots. Which p minus 1 roots? 1, 2, 3, all the way to p minus 1. Okay, so first let me do an example and then we can prove this theorem. Example, let's say you want to find 7 to the power 222 mod 11. Seven to the power 222 mod 11. If you want to find this number, so we can use Fermat's little theorem. Fermat's little theorem says a to the power p minus 1 is always equal to 1 mod p, which means a to the power p minus 1 is congruent 1 mod p. Now, what is my p? What is the prime number here? So here p is 11. Every calculation is done mod 11. So my p is 11. So by Fermat's theorem above, Fermat's little theorem, what can I say? I can say that 7 to the power 10 equals 1 in Z11, or i.e. 7 to the power 10 congruent 1 mod 11, right? So now what does this imply? So this means that 7 to the power, if I raise both sides to power 22, congruent 1 to the power 22 mod 11. So that means 7 to the power 220, congruent 1 mod 11. So 7 to the power 220 is congruent 1 mod 11. What do I need? I need 7 to the power 222. What do I have? 7 to the power 220. So I just need 2 more powers of 7. So if I multiply both sides by 7 to the power 2, I get 7 to the power 222. Congruent 7 to the power 20 is congruent 7 to the power 2 mod 11. 7 to the power 2 means 49. And what is 49 mod 11? It's 5, right? Because 11 divides 49 minus 5. 49 minus 5 is 44, which is divisible by 11. So there you are. So that means 7 to the power 222 equals 5 in Z11. Or you could say congruent 5 mod 11. So we could easily solve this problem because Fermat's theorem guaranteed that 7 to the power 10 is 1, and 1 to any power is luckily 1. So from 7 to the power 10, we could jump to 7 to the power 220 by just raising both sides to the power 22, and 1 to the power 22 is 1. Once we got 7 to the power 220, we needed 7 to the power 222, so we just needed to multiply both sides by 7 to the power 2. And that's it, we got 7 to the power 222. Okay, now let's see how we can prove Fermat's little theorem. So proof of Fermat's little theorem. So first, we prove a theorem called Wilson's theorem. So see, these are mentioned in your book exercises, but I found them too much if I also leave them to all for exercises. These are important theorems, and sometimes the proofs are tricky, especially because you have no background of number theories, like your first course, right? So that's why I don't want to leave them as exercise like your book did, and I'm basically explaining and proving them here. So that in this section, so this section is long, and especially the exercises. There are so many important concepts and with sometimes tricky points and tricky proofs, all included in the exercises. And like I said, because it's like your first course in number theory, I want to prove them and derive them for you during lectures.